ebidole lecture sef. Onye n'aka.
Good morning. Good morning.
Good morning, sir.
Yeah. Barika the Salah.
Yes, sir.
I hope we are enjoying our Salah break. So we are starting the
Those
class.
that are not speaking, please mute.
Please kindly mute yourself so that we can enjoy ourselves this morning.
Okay, which one is your device? Lenovo.
My own is Lenovo.
I can mute other.
Please kindly mute others. My own is Lenovo. Yeah, good morning once again.
Good morning, sir.
Actually, I had wanted this class to start 7:30, but the class rep suggested 8 because I also have some other things I want to do, but there's no problem about that. That is the reason why we will not wait for others. We are going to start immediately. It is already 8 o'clock. This is 8:01 now. So this morning we are looking at the third aspect of our course, which has to do with the principle of applied and general electronic and circuit diagram. So this morning we are going to be looking at the principle of applied and general electronic. The circuit diagram will be for another day, will be for the fourth lecture. So in this course, we are going to be using what we call SI unit. That is a standard unit of measurement in engineering and science. And I think we have been using it. We used it the last time we had class on the calculation for centrifuge, which I asked we need to convert from radians, from seconds to from minutes to seconds and the like, for kilogram, from gram to kilogram. So those are the standard unit of measurement when it comes to science and engineering. So these are the units. When we talk about length, the unit is meter, and it is represented with capital letter M, mass, kilogram, kg, time, seconds, x, so and so on and so forth. So we also have some derived unit. These units are derived from the SI unit, like velocity, for instance, is measured in meter per second. Meter is already an SI unit. The second is another SI unit. You derive the unit for velocity with these two, so meter per second. The same thing applies to acceleration, which is meter per second squared. So now in engineering and science, we use prefix to identify some units. Like when you talk about mega now, that is 10 raised to power 6 kilogram, kilo rather, not kilogram. That's 10 raised to power 3. When I say 10K, 5K, that is 5,000, 7,000. So that is what K represents, 10 raised to power 3. Then when we are talking about the units that are so small, then we'll be talking about milli times 10 raised to power minus 3, micro times 10 raised to power minus 6, nano times 10 raised to power minus 9, and pico times 10 raised to power minus 12. So we are going to be employing all these as we proceed in our lecture. So we are talking about principle of applied electricity and electronics. So we are going to be talking about conductor and insulator. What is a conductor? A conductor is a material that allows electric current to flow easily through it, whereas an insulator is a material that does not allow electric current to flow through it. And the two of them, they have application in engineering and science. So an example of a conductor is a copper. So copper is a good conductor of electricity, and that is why it is being used in so many applications. Other conductors are aluminum, silver, gold, and the likes. So insulators, as I've said, they don't allow electricity to pass through them easily. It is opposite of insulator. And we have example like glass, plastic, rubber, air, and wood. So in between the insulator and a conductor, we have another material that is called semiconductor. But insulator and conductor, they have applications in engineering. Insulator, for instance, now is used to protect us from dangerous effects of electric current flow. That many cables, wire, when you see them, they are insulated. They use another material to cover them up so that it can protect us from electric shock, as we have discussed in our first lecture under workshop practice. So conductor have a very low resistance to electric current, while an insulator have a very high resistance to electric current. The two factors become very important when we start to deal with actual electrical circuit. Now, I made mention of semiconductor. We can understand this better when we look at what we call resistivity. The electrical resistance of an electric or electronic component or device is generally defined as being the ratio of voltage difference across it to the current flowing through it. We are going to talk about Ohm's law, not Quetelet. But resistivity is just the ability, the capacity of a material to prevent the flow of electric current through them. And it is measured in rho, which is ohm meter, ohm, which is an inverse to what? To conductivity. It is inverse to conductivity. So if the resistance of the various materials is compared, they can be classified into 3 groups: conductor, insulator, and semiconductor. So let's look at this chart now, the resistivity chart of materials. The first one at the down here is the insulator. For the insulator now, we say that they have high resistance to flow of current. So for quartz, for instance, now it is having at 7.5 times 10 raised to power minus 8. That is ohm per meter, according to the unit that we saw here, ohm per meter. Then glass, it has 1 times 10 raised to power 10. That is quite high too. But when we look at conductor, which is here, carbon, gold, silver, all these are conductor, and these are their resistivity. 3.5 times 10 raised to power minus 5 for carbon. That means very, very low when you compare it with insulator. Gold, 2.4 times 10 raised to power minus 8. Silver as well, 1.6 times 10 raised to power minus 8. And that of this copper. That of copper is it's not included here, but that is very low. And that is why copper is a good conductor of electricity. So in between the conductor and the insulator is another material called a semiconductor, which also has a very good application in engineering. By the time we talk about diodes, transistor, and the likes, we know where this semiconductor come in. So semiconductor, they have property in between the conductor and insulator. And they are, as I've said, they have a very wide application in engineering because of their unique characteristics in terms of their resistivity. Now, let's begin to take these materials, component of electronic material. Let's take them one by one. So maybe we'll talk about the resistor, capacitor, and maybe diode for the purpose of this class. So resistor, they are most commonly used in electronic circuit. They are very important, but at times they are being overlooked. So to the point where they are almost taken for granted. So we have many different types of resistor that is available based on their property and based on the manufacturer. We have a very one that is very small, that is mounted on the chip, and we have a large one that is wounded on a particular material. So the principal job of a resistor within an electric or electronic circuit is to prevent or resist the flow, and at the same time you can say it impede the flow of electrons through them by using the type of material that they are composed from. Resistor can also act as voltage dropper or voltage divider in a circuit. The essence of a resistor in a circuit is to resist the flow of current. Maybe a particular component, for instance, now require something like 0.2 milliamps, and the current that is flowing maybe from our power supply now is something like 13 amps. How do you achieve that current so that it will not blow off the component or the whole circuit? So we can use a resistor. The resistor will absorb the majority of this current that is flowing, whereas the one that is required to be flown to that particular component will be allowed to pass through. That is just the function of a resistor. So in electrical and electronic circuit diagram or schematic diagram, the most commonly used symbol for a fixed value resistor is using the zigzag, and this is the zigzag. So a resistor can be represented like this, and at the same time, it can also be represented. I hope we are seeing my slide.
Yes, sir.
Okay.
Yes, sir.
Thank you. So these are the two. We also have some other circuit symbol or schematic symbol of a resistor. We are going to see them, but majorly, if I want to draw a circuit now, it's either I use this one, the zigzag mode, or this block mode. When connecting a resistor can be connected in series, in parallel, or combination of series and parallel. And when we connect resistor like that in an electronic circuit, there's a need for us to find the equivalent resistance of that particular resistor. So we are going to be looking at resistor being connected in series, in parallel, and at the same time when you have combination of parallel and series. Now, if you connect a resistor in series, it means that they are basically chained together in a single line. This is an example. This is an example of resistor connected in series. This is the first one, joined with this one, joined with this one. That tells us that the same current flow through the three resistors. Now, Since all the current flowing through the first resistor has no other way to go to it must also pass through the second resistor. What we are trying to say that there is no division here. The current passes through here. There is no other route that can flow out. It has to pass through this one, then pass through this one, then pass through the third one. So the same current will flow through the three resistors. So resistors in series have a common current flowing through them. We have to understand that any resistors that are connected in series, the same current, if it is 1 milliamp that flow from resistor A to resistor B, that means it's the same current that will flow through the two of them. Then the amount of current that flow through a set of resistors in a series is the same at all points in a series connection or in a series circuit. For instance, for this one now, IR1 will be equal to IR2 will be equal to IR3. But the voltage across them will depend on the value of each resistor. For instance, the one with higher value, the voltage that will drop across it will be higher than the one that has a lower value. R1 here is 1 kilo ohm. Remember, I said K means times 10 raised to power 3. That is where we started from this morning. So 1K means 1,000 ohm. 2K ohms means 2,000 ohm. And 6K ohm means 6,000 ohms. So the one with higher resistance will do what? We have a higher voltage drop across them. So the equivalent resistance of a resistor connected in series is the same thing as R1 plus R2 plus R3. I hope we are following.
Yes, sir.
All right. Now, we have said that the voltage that pass across each of the resistance will be varied depending on the value of each resistor. For R1 now, from our Ohm's law, we are still going to go to Ohm's law, but we need to apply it now. From our Ohm's law, we know that R will be equal to I multiplied by R. That is the voltage across R1 now. That's what I'm trying to say. Voltage across R1 will be equal to current times the resistance, which is 1 milliamps times 1 kilo ohm. Milliamp is times 10 raised to power minus 3. K is times 10 raised to power 3. So the two of them will nullify each other. So we have 1 ohms. And the one that passes across the R2, we have what? 2 times 1, which is going to give us 2 volts. Remember, K and milli as what? As cancel each other. So the last one, we have 1 times 6, we have 6 ohm. So the total voltage now across this circuit from A to B will now be sum of the voltage of R1, R2, and R3, which is 9 volts. Now, let's look at this example. Calculate the equivalent resistance, series current, voltage drop, and power for each resistor of the following resistors in series cycles. This resistor in this particular circuit, they are connected in what? They are connected in series. Why? Because this one is directly connected to this one. This one too is directly connected to R3. R1 connected to R2, R2 connected to R3. So the current that is flowing does not have any other route to flow down one direction like this. So that is why we say that the current that passes through a series resistor in a particular circuit is the same thing. The one that passes through R1, pass through R2, pass through R3, but the voltage will differ depending on the value of the resistor. Now, if we want to calculate this now, we use our Ohm's law, which we are going to talk about later. Ohm's law just say that phi is equal to RR, where phi is the voltage, R is the current, and R is the resistance. Now, for R1 now, the value of R1 here is 10 ohms. So if you want to calculate the current in R1, you just say that voltage is what is divided by R. But we cannot use that voltage divided by R because voltage we drop across. We cannot use 12 for all of them. If you want to use 12 now, that means you find the equivalent resistance. And what is the equivalent resistance? You just say R1 plus R2 plus R3, which is going to give us 60 ohm. That is 10 plus 20 plus 30, which is 60 ohm. And that is why they get our RT, which is R total, as 60 ohms. Now, if we know our RT to be 60 ohms, then, and we know the voltage that passed across it to be 12 volts. And at the same time, we say that the same current will flow. So our RT is what? 60 ohms. So, and our Vs is 12 volts. So we can now say I is equal to V divided by what? Divided by R total, in order for us to get the current that flows through the whole circuit. And if you have your calculator, if you do that, you say 12 divided by 60. You'll be getting something like 200 milliamps. So our V1 now, voltage will be different. V1 will now be equal to, you know, our Ohm's law is phi is equal to IR. So our I will now be equal to phi, which is, okay, want to calculate phi now. Just say 10 multiplied by 200 milliamps, which will give you 2 volts. From Ohm's law, phi is equal to IR. For R2 now, 200 milliamps multiplied by 20 will give us 4 volts. And for R3, the voltage that flow across RT is going to be 200 multiplied by 30 ohms, which is going to give us 60 volts. So we can try and check this one out when we get after this lecture. So if you have any questions, then we'll look at it together. Then the issue of power, let me silent about it now until we get to the slide that concerns power. Now, in summary, the resistor in series, when two or more resistors are connected together end to end in a single branch, they said to be connected together in series. Resistor in series carry the same current. There's no doubt about that. We have emphasized that it carries the same current. But the potential difference, which is the voltage across each one of the resistors, are not the same. So in a series circuit, individual resistors add together to give the equivalent resistance. That is R1 plus R2 plus R3 plus R4, depending on the number of resistors. So the resistor in a series circuit can be interchanged without affecting the total resistance, current or power to each resistor. So in as much as it is connected in series. Please, any question before we move to resistors in parallel? Do you have any question? So far, so good. Are we together?
Yes, sir.
Okay. Now, resistors in parallel. Resistors are said to be connected in parallel when both of their terminals are respectively connected to each terminal of the other resistor or resistors. Now, this is an example of a parallel connection. This is a resistor here. It is connected to the circuit like this. Another resistor in the same direction connected like this. This also connected like this. So the current that flows now, current will flow this one. Part of the current will go ahead, enter this one. Part will go ahead and enter this one. So in other words, the current that flow to a resistor connected in parallel is what? Differs. It differs because it is connected in parallel. As current flow here, the remaining current will flow through this place. Another one we manage to escape and flow through R3. However, the voltage is what? Is the same, just like the opposite of a resistor in series. So in previous series connection circuit, we saw that the total resistor R3 of the circuit was equal to the sum of all individual resistors added together. But in parallel connection, when you want to look at the equivalent resistance of the resistor, you use what? You use the reciprocal. 1 over RT, that is R total, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Then until you get to the last R. Now, if we now want to get the equivalent, now find the reciprocal, now find R3, will now be equal to the inverse of whatsoever answer that you might have gotten. So the equivalent resistance is always less than the smallest resistor in parallel network. So the total resistance RT will always decrease as the additional parallel resistor are added. What we are trying to say here is that if you, let's look at this, okay, before I move to that place, these are the various ways by which resistors can be connected in parallel. This one, A, for the first diagram here, A is in parallel with B. And for the second one, A, B, C, and D, they are in parallel. And this third one, A, B, and C, they are also in parallel because this is the voltage or the current source. It will divide to each of the resistor. And it can also be connected in triangular form, A, B, C. All these one, they are parallel connection of resistor. Let's look at this example together. Find the total resistance RT of the following resistor in parallel network. R1 is equal to 200 ohms, R2 is equal to 470 ohms, while R3 is 220 ohms. So the total resistance RT across the two terminals A and B can be calculated as follows. Just say R1 over RT, which is your total resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And we said R1 is 200, so it's going to be 1 over 200 plus 1 over 470 plus 1 over 220. And when you do it, you should get 0.0117. Now, for you to now get the resistance now, just find the reciprocal of 0.117, which is going to give you 85.67 ohms. 85.67 ohms. Are we following, please?
Yes, sir.
Yes, sir.
Yes, sir.
All right, thank
We are
you.
following, sir.
Thank you so much. So, but if you are having just only two resistors, instead of you saying 1 over R1 plus 1 over R2, you can actually use this formula. RT is equal to R1 multiplied by R2 divided by R1 plus R2. It will still give you the same answer as saying that 1 over RT is equal to 1 over R1 plus 1 over R2. Then you now find the inverse of it when you get your answer. So it's going to, but this formula, I have tried it. It doesn't work for when you have more than two resistors connected in parallel. If you have like 3 now, it might not give you the accurate answer. So it will only work for 2 resistors connected in parallel. Let's look at this example again. Consider the following circuit with only 2 resistors in parallel combination. Using our two, okay, the essence of this example is just to use this formula. So using our 2 resistor formula above, we can calculate the total circuit resistance RT. Just say RT is equal to 22 multiplied by 47 divided by 22 plus 47. So if you do it well, we should get something like 14,985 ohm, which is equivalent, I say, 14.9 kilo ohms. Now, at time in an electric circuit, you can have the combination of both series connection and parallel connection of resistance. But before we look into that, let's look at the current in a parallel resistor circuit. Now, we said that the current differs. So the total current RT in a parallel resistor circuit is the sum of the individual current that flows in the parallel branches. So the amount of current flowing in each parallel branch is not necessarily the same as the value of the resistance in each branch. The value of each resistance in each branch determines the current within that particular branch. For example, now, although the parallel combination has the same voltage, we have said that the resistance could be different. Therefore, the current flowing through each resistor will definitely be different as determined by Ohm's law. Now, when we consider two resistors in parallel, and by using Ohm's law, the current flowing through each resistor can be different. Using this example now, R1, 22 kilo ohms, and R2, 47 kilo ohms. Then you can now say that the current that flows through R1, using our Ohm's law, is equal to V divided by what? Divided by R1. And our voltage, we say that it is the same. It is 12 volts. You can now say 12 volts divided by 22 kilo ohm. Then we are going to get 0.54 milliamps. So the same thing applies to R2. Our voltage is 12 volts. The same voltage flows through it. So far, it is a parallel connection. Then divide by 47,000 kilo ohm, which is 0.255 milliamps. Now, to get the total current that flows through particular circuit, you just need to add the current that flows through R1 plus the current that flows through R2. Will give you the total current that flows through that circuit. So RT is equal to 0.545 plus 0.255, which is going to give us 0.8 milliamps. Or if you want to take it to microamp now, that's 10 raised to power minus 6, you get 800 microamps. So we can do this one at our own lesser time when we have the slide with us. Just calculate the individual branch current flowing through the following resistor in parallel circuit and the total current that flows through it. So we don't need to submit it, we just use it to practice. Now, in summary, for resistors connected in parallel, it means that when two or more resistors are connected so that both of their terminals are respectively connected to each terminal of other resistor or resistor, they are said to be connected together in parallel. The voltage across each resistor in the parallel combination is the same, but the current flowing through them are not the same. Let's just have that at the back of our mind. Then the equivalence or total resistance RT of a parallel combination is found through reciprocal addition of the total resistance value will always be less than the smallest individual resistor in the combination. So we can use this as a check. When you get your total resistance in a particular circle that are connected, for a resistor that are connected in parallel, your total resistance value should be less than the smallest the resistance value of that particular resistor. So if it is higher, that means you need to check the calculation again. It might be wrong. So when you now have the combination of circuits that has series and parallel connection. How do we go about it? So for example, we can be asked to calculate the current I taken from the 12-volt supply in this particular cycle now. This cycle now, we have both series and parallel connection. R2 and R3, they are what? They are in series. Whereas the combination of R2 and R3 is in parallel with R4. Are we following, please?
Yes, sir.
Yeah,
Yes, sir.
R2 and R3, they are in series now. But the
Yes.
combination of them, by the time you find the resistance
Yes,
of
sir. We
R,
are following.
okay, thank you, sir. By the time you find the resistance of R2 and R3, they are now in parallel with R4. When you now find the equivalent resistance of R2, R3 in parallel with R4, then they now form a series connection with R1. So let's look at it. Let's look at it. Now, R2 plus R3 now is 8 ohms plus 4 ohms. We give us 12 ohms. That means we have found the equivalent resistance of R2 and R3 because they are connected in series. You just add them together. Now, we have reduced the cycle now. Our resistance, total resistance of R2 and R3 is 12 volt. We have made it to what? To be RA now. So now we can replace both R3 and R2 and R3 with what? With a single resistor of resistance value of 12 ohms, which is this RA now. Now, RA is now in what? It's now in parallel with R4. Now, let's calculate RA and R4 in parallel combination. So RA and R4, we can now say 1 over RA plus 1 over R4 is equal to 1 over 12 plus 1 over 12, which is will give us 1 over whatever answer we get. We now find the inverse, which is give us, if you calculate it very well, it will give us what? 6 ohms. So we have been able to reduce that again. Now, this RA and R4 now, we have been able to reduce it to what? To one single resistance value of what? Of 6 ohms. So we can now draw another cycle. So our R combination now is now equal to 6 ohms. Now we can now find the total resistance now, because R combination is in series with what? With R1. So once they are in series, we just add it together. So we are going to have R1 plus R combination, which is 6 plus 6, which will give us 12 ohms. 12 ohms. So the total resistance of this circuit where we started from, this is the circuit where we started from, we have been able to reduce it to one single resistor value, which is 12 ohms. That is our R equivalent, 12 ohms. And because the voltage that is applied to it is what? 12 volts. So we can easily calculate the current now using our Ohm's law. So our current is just P divided by R. That is voltage divided by resistance, which is 12 divided by 12. So we get 1 ampere. The unit of current is what? Ampere. So we get 1 ampere. Do we understand that example, please? Hello, class. Are we following?
Yes.
Okay.
Yes, sir.
All right. Thank you. So
Yes,
let's move. Okay. Thank you. So let's move a step further. Let's look at resistors color code. Now, in practice, if you want to buy resistor in market, all these small resistors that we use in electronic cycle, they are color coded. They are color coded. So if you want to buy 1K ohms of a resistor now, you need to be conversant with color coding. It is the color code that we use to get the value of the resistors that you want to get. Maybe you are working with a particular circuit and one of the resistor is burnt. How do you know the value of that resistor? So that by the time you go to Ogunpa market in Ibadan, for instance, to get a resistor, what will you tell the person that wants to sell it for you? This is the value of the resistor that I want to buy. So this is where resistor color code now come into place. Now, standard color codes, we have different bands of resistor. We can have four bands, we can have 5 bands, we can have 6 bands. But what we need to know is that the first 3 bands of resistor, they are what? They are the digit number. They are the digit number. That is, if you have red, yellow, blue, for instance, now, you are going to represent those ones with digits, which could either be 0, 1, 2, 3, 4, 5, 6, up to 9, depending on the color. Depending on the color. The second band also is for digits. The third band is for digits. While the fourth is what? Is the multiplier. This is where the kilo ohms, the mega ohms comes in. The milli ohms comes in. You multiply whatever value that you have gotten from your first, second, and third digit. You multiply. Whereas the fifth one is the tolerance. The essence of the tolerance is that if you want to buy a resistor of, well, let's say 1 kilo ohms, for instance, now, which is 1,000 ohms, if you don't get the actual value of that resistor, there is tolerance. And the tolerance, it could be 10%, maybe plus or minus 10%. So if you get something like 900 ohms, you are good to go. If you get something like 1,000, 10 ohms, 110 ohms, 1,010 ohms, you are good to go, depending on the tolerance. Whereas the last band, which could be the 6th band, is what? Is temperature coefficient. The temperature coefficient of the resistor. So let's look at this. So the color coding start with black to white. And black is represented with 0, which is a digit. So let's say the first digit is 0, the second digit is 1, the third digit is 2. So you have 0, 1, 2. So that means you have 12. But that 0 does not count at the beginning. So you have 12. So if your multiplier is now 1,000, which is orange, just as that is 12 multiplied by 1,000, you have 12 kilo ohm resistor. So that is the way to get the value of a resistor that is color coded. So the best way to understand it is using this formula. A way to remember the colors: bad boys read our young goat, but they usually call it girls now. I mean before, but I don't know the reason why they changed it. So bad boys rape our young goats, but violent goes willingly. So whereas B, the first B stands for black, as we have it there. The second B stands for brown. Then R stands for red, orange, yellow, just like that, and so on. So let's look at this sample. The resistor color code system is all well and good, but we need to understand how to apply it in order to get the correct value of the resistor. The left hand, which is the most significant part of it, is the color band. Is the band which is nearest to a connecting lead with the color coded band. So digit multiplier. So if we have digit multiplier, this is for 3 color coded resistor now. For example, a resistor has the following color marking: yellow, violet, and red. From our chart here, which we need to know, from our chart here, yellow stands for, what is the value of yellow here in digits?
4.
4. Okay, so let's go back. Yellow stands for 4. Then foul length. What is the value of foul length here?
7.
7. Good. So there are 7 here. Now, the third one now is the multiplier, because it's just a 3-colored band resistor. So the third one is a multiplier. That means the value of whatever you get, you multiply it by what? By 100 or by the number of zeros. So let's go back to our chart. Now, red is the last one. And red is what?
2.
Not 2. We are looking at the multiplier now. It's what?
Okay.
100.
100. So we are going to multiply it by 100. That is why they say 4, 7, that is 47 multiplied by 100. We now get 4,700 ohms, which is the same thing as what? 4.7 kilo ohms. 4.7 kilo ohms. This is a 3-band resistor. That is why we are not taking the third value as what? As digits. So if it is a 4-band resistor now, the third value will be taken as digit also, where the fourth will be the multiplier. Yes, do we get that?
Sir.
Yes, sir.
All right, thank you, sir. So if a resistor has no fault tolerance band, then the default tolerance will be 20%. That is general. So if you are not giving the tolerance band, then you can use 20% as your tolerance, which means if you add 20% of whatever value that you have gotten and you get to the market, you don't get the actual value and you get the one that is at least addition of 20%, it is good to go. If it is minus 20%, you are also good to go. So, but the formula to easily remember all this is this what we call bad boys raise our young goats, but fouled goes willingly. So who has control for this slide that is putting a line here? Please help us remove the line. Now let's move forward. Direct current. What do we mean by direct current? So voltage is the potential energy of an electric supply stored in form of an electric energy. So voltage can be thought as a force that pushes electron to a conductor, and the greater the voltage, the greater is the ability to push the current through a given circuit. So if we have a conductor, for instance now, and you apply a voltage at one end, so the potential difference, that is the energy to move that electron from one end to another point within that conductor or within that circuit, is what we take as what? Potential energy. So as energy has the ability to do work, this potential energy can be described as the work that is required in joules to move electron in the form of an electrical current around the circuit from one point to another. So the difference in voltage between these 2 points in a circuit is what we call as potential difference. Potential difference. So the potential difference between 2 points is measured in volts with the symbol V, capital letter V, or at times some people can use a lowercase letter. And the energy E with a lowercase e is sometimes used. Energy, when you want to write the energy, you can just say E is equal to so, depending on the formula that you are using. So we are still going to get to the formula. So the greater the voltage, the greater is the pressure. That is the force. The greater the force that pushes the electron, and the greater work will be done. So a constant voltage source is also called a DC voltage. You know, our electric current in homes, the one that is supplied by Abidec or Ecodex, depending on which distribution company that apply to us. What they give us is what? Alternating current or alternating voltage. And the value is what? 220 volt. But when we talk about direct voltage or direct voltage, that one does not alternate. It passed through a straight line. So we are going to look at it. So example of where we can get a direct current is our what? Is our battery. We have 5-volt battery, 12-volt battery, 24-volt battery. The battery that we use for our car is an example of a device that provides a direct current or a direct voltage. Our appliances in the laboratory, they also use what we call direct current, but there is what is called a rectifier inside each electronic cycle, so that by the time you pass through or you plug in your device to a 20-volt power supply, for instance, there is a power supply unit inside inside these medical devices that does the rectification and channel the voltage to the required voltage to each of the component inside the electronic cycle. Inside the same medical device, some component may need 5 volts, another one may need 12 volts, another one may need 24 volts. So there is a power supply unit that does the rectification, that converts the alternating current back to direct current. And a majority of hospitals today, we are using solar, renewable energy. How do we be able to accomplish this? Solar will give you comfort. Your inverter will convert your DC that your battery has stored, maybe 12-volt batteries, 24-volt batteries connected in series. Your inverter will now convert it back to the alternating current so that we can use it through our socket. So the main voltage supply in Nigeria, not Ethiopia this summer, is 220-volt AC, while that one in America is what? 110 volts. So if you buy an electronic device from United States and you bring it home to Nigeria and you plug it directly to our own power supply here, it will just got burnt immediately, because you are using a 220 volt as against the 110 volt that is required for that particular devices. So these are the symbols of voltage. The first one is a single cell. We call it, when you have 2 or more cells, then they become battery. So a single cell, this is the circuit symbol. The longer terminal here is the positive terminal, whereas the the shorter one is the negative terminal. So when you have 2 of cells together, then it becomes a battery. So instead of representing it 2 like this, then you can represent it with this sign as what? As a DC voltage source with plus and minus. The plus so that this is the positive side, and the minus so that this is the negative one. Then for the alternating voltage source, that one, the one that we get from our public power supply or the one that we got from our generator at home, it is sinusoidal. We saw that what? It is fluctuating. It is not, it is alternating. It is not a direct, it is not in a straight line. And we represent it with this alternating sign. This is the AC voltage source. Electric currents. We have talked about the voltage now. Electric current is the movement or flow of electric charge, and it is measured in amperes with the symbol I for intensity. I, if you want to calculate current now, you can just say I. We have been using it, we use it in the resistors example. Just say I is equal to V divided by R. I is the current, C is the voltage, and R is the resistance. So conventional current flow. How does current flow in a circuit? Current flows in a circle from, please, who is doing this? Who is Adedapo? Adedapo, you are the one that is putting series of lines on the slide. Please, can you remove it?
Please remove it. So, Elijah, please remove the lines. And just use your eraser. Remove it. And then you disable your annotation marker.
Elijah, disable your allocation marker and erase the line that you are putting on the slide, please. So, conventionally, this is the flow of current in a circuit. Current flow from the positive end, the positive terminal, then through the circuit to the negative terminal. Whereas electron, on the other hand, the direction of flow is opposite to the direction of flow of electric current. It flows from the negative terminal to the positive terminal. So current that flows in a single direction is what we call direct current or DC. And current that flows or that alternates back and forth through the circuit is what we know as what? Alternating current or AC. So using the tank of water relationship now, current is the equivalent of the flow of water through the pipe, with the flow being the same throughout the pipe. You know, when you open your tap water at home from the storage now, water tends to flow from the tank to where you want to maybe to your bucket, for instance. Now, we can equivalent that to the flow of electric current. So the faster the flow of water, the greater the current. So any current source, whether DC or AC, like a short or semi-short circuit conductor, but what? But it's any open circuit. So current will flow through a DC or AC circuit. But when it is open means you switch off. When you switch off your light at home now, when you switch off the socket or you switch off the switch, then you are disconnected from power. So an open circuit is what? Is a circuit that is disconnected from power. Hence, current will not flow through that particular circuit. So the resistance of a circuit is the ability. We have talked about resistivity before. We have talked about the resistor before. So, but let's just look at it in the context of what we have discussed. So the resistance of a circuit is the ability to resist or prevent the flow of current through it, making it necessary to apply a bigger voltage to the circuit to cause the current to flow. So resistance is measured in ohms. I think we have talked about that. We have used it in example. Ohms, which is the symbol of omega, with the prefix used to denote it. You can have kilo ohms, as you have said, mega ohms, pica ohms, depending on the value. So these are other symbols of resistor. We have talked about the first two before. This is another one, which is used for variable resistor, or you call it a potentiometer. Then another one for variable resistor, which is called rheostat. Then when you have light dependent resistor, this is just the sign of light. So these are the various symbols for a resistor. Now, let's go back to our Ohm's law now so that we have better understanding of the application or the examples that we have done before now. So when we talk about Ohm's law, what does Ohm's law say? Ohm's law just says that the electric current that flows through a conductor or an electric circuit is directly proportional to the applied voltage and at the same time inversely proportional to the current, inversely proportional to the resistance. So phi, current is directly proportional to voltage and at the same time inversely proportional to the resistance. So the relationship between voltage, current, and resistance form the basis of Ohm's law. It forms the basis of Ohm's law. So if we know any of the two, then we can calculate the third one. So Ohm's law is used extensively in electronic formula and calculation. So it is very important to understand and accurately remember this formula. So Ohm's law, you just say that phi is equals to IR. Phi is equals to I times R, where phi is in volts, R is in ampere, and R is in ohm. Then our current we said that is inversely proportional to what? To resistance. So I is equals to phi divided by R. Then R now, R also is equals to phi divided by R because I and R, they are inversely proportional to each other. So to have a better understanding of this Ohm law, there's what we call Ohm's law triangle. Ohm's law triangle. Whereas the one that is at the top is what? Is what you say that for this particular first triangle now, you just say that phi is equals to the two that are under it. V is equals to IR. Phi is equals to IR. So phi is equals to IR. Then, if you know phi, then you can calculate. If you know any of the two, then you can calculate the third one. Now, phi is equals to IR. We circle phi here. Now, I that we circle here is so that phi, I is equal to phi divided by R. Are we getting it? This I that is darkened here, or that is highlighted here, is showing that V is the what? Is dividing R, which so that I is equal to V over R. The same thing applies to the R here, which is the resistance. It's saying that V is equal to what? R is equal to V divided by R. Are we following? The essence of the triangle is just to be able to remember this formula easily. Although it is simple, it's something that we are used to even from our secondary school. Any question on the Ohm's law triangle or anything so far?
No, sir.
Any question? Are we following?
Yes, we are, sir.
All right.
Yes.
Thank you.
No question.
All right. Thank you. Now, I silent about the issue of power in the particular example the other time. So let's look at the power now. Power in an electronic circuit. Electrical power, P, in a circuit is the amount of energy that is absorbed or produced within that particular circuit. So a source of energy such as voltage will produce or deliver power while the connected load absorbs it. So when you connect a circuit or a device to a voltage source, it will definitely produce energy. And that energy is as a result of power that is provided by that voltage source. So the symbol, the quantity symbol for power is P, and the product of voltage multiplied by current with the unit of measurement being wattage. So the unit of measurement of power is wattage, which is represented by capital letter W. Then we can have milliwatt, which is times 10 raised to the power minus 3 kilowatt, and megawatt, depending on the value of that power. So as we have done for Ohm's law, we can also do the same thing for power using our formula. Ohm's law says that phi is equal to RR, and you say that R is equal to phi over R, and R is equal to phi over I. So using that same formula, our power now, power is the product of voltage and current. P is equal to I multiplied by phi. P is in wattage, phi is in foot, and I is in ampere. Now, using our Ohm's law, we can decide to do what? To change the voltage here. We know that from our Ohm's law, phi is equals to IR. So we can slot IR here instead of phi. So if we slot IR here instead of phi, we are going to be having I square R, which is here. P is equals to I square R is what? Is also acceptable. So if you are given I and R in a particular circuit and you are asked to calculate the power, you should be able to calculate it by manipulating your formula. And at the same time, we know that I, in our own law, that I is equal to V over R. So I can decide to change this I that is here now to V over R. If I do so, I will be having V multiplied by V divided by R, so which is phi squared divided by R. So this is also acceptable. So if you are given the voltage and you are given the resistance, you can be asked to calculate the power in a particular circuit. So again, we can use the three quantity to do what? To have what we call power triangle, as we did for Ohm's law. And this is our power triangle. P is equal to IV, which is this. If you take your I now, it's the same as say I is equal to P over V. And if you take your V, using your triangle, you just say that phi is equal to P over R, which is what we have here. So the unit of power is in wattage, which is represented as watt, as we have said. And at the same time, in some machine or devices that use electric motor, we can use horsepower. Our AC, for instance, now is rated in horsepower. And 1 horsepower is equals to 746 watts. So we might need to do some conversion at time. Just know that 1 HP, which is horsepower, is equals to 746 watts. So let's look at this example. So we can apply this example to the previous example of power that we decided not to mention. So when you are reading through the slide, you can now look at it. So for the circuit shown below, find the voltage phi and the current I, the resistance R, and the power. So for the voltage from our own song, we know that V is equals to IR. What is our high? Is 2. What is our R? Is 12. So we have what? 24 volts. And that is why they get 24 volts here. Now, assuming they didn't give us current now, and you know your voltage and you know your R, you can calculate your current. Current is what? V over R, which is 24 volts divided by 12 ohm, which is 2 amps. So in case you are not giving the resistance now, but you are giving the current and the voltage, so you can calculate your R. R is equal to V divided by R, which is 24 divided by 2, which is 12 volts. Now, power. So we have all our three parameters. We have our voltage, we have our current, we have our resistance. We can use any of the formula of power, this one, to get it. So power, please mute yourself, bag.
Oh, sorry, sir.
Thank you. P is equal to IV. What is our I? Which is 2 amps. What is our V? 24. So we have 48 watts. So that is electric power. What about the electric energy? Electric energy is the product of power and what? And time. The product of power and time. So if power is measured in wattage and time in seconds, then electric energy is measured in watts per second or joules. So if power is measured in kilowatts and time is in seconds, then electric energy is what in kilowatts. So our unit of power, if you want to recharge your prepaid meter now, they will give you in kilowatts, 33 units. It's saying that 33 kilowatts hour. That is what they have given you. So that is the unit of energy, because you are buying energy. It's the energy that will now give you power to use at home. So electric energy in ohms records the number of kilowatt hours used and is thus an electric or energy meter. Let's look at this example for power and probably energy. It says that a 12-volt battery is connected across a digital weighing scale, having a resistance of 40 ohms. Determine the current in the load, the power consumed, and the energy dissipated in 2 minutes. This is a very simple question. Determine the current. We have the volts, we have the ohms, which is resistance. From our Ohm's law, we know that I is equal to V divided by R. That is, I is equal to 12 divided by 40. So what is going to be our answer? 12 divided by 40 will give us 0.3 amps. So they say we should also calculate the power. From this one, we consider we know our I, we know our V, we know our R. Our power is equal to IV. IV, that is 0.3 times 12, which is give us 3.6 watts. Now, the energy now, we say that energy is equal to power multiplied by time. We have gotten our power here to be 3.6. And they are saying it is used for how many what? For 2 minutes. Remember, we need to convert the minutes back to SI units of time, which is in seconds. So 3.6 multiplied by 2 multiplied by 60, because we are converting to seconds. 60 minutes, 60 seconds with 1 minute. So when you do that, you get 432 joules. The unit of energy is in joules or watt seconds or joules. But it's better you use joules. Do you have any question on that example? All right.
No,
Let's
sir.
look at thank you. Let's look at another example. A laboratory autoclave consumes 3.6 megajoules. What is megajoules? What are we going to multiply with when you are doing calculation? Megajoules, from what you have said so far.
We multiply the joule by 1,000.
Mega. No, ma.
That is the passive.
K is 1,000.
Kilojoule is 1,000.
Yes, but we are dealing
But
with
this is
megajoules now. Capital letter M. So what are you going to multiply it with? We are going to multiply it with 10 times 10 to the power 6. That is 1 million.
Times 6.
Yes, 10 raised to the power 6.
1 million.
Now, elaborate. Let's go back to the question now. That is 1 million. A laboratory autoclave consumes 3.6 megajoules when connected to a 250-volt supply for 40 minutes. Find the power rating of the heating element used for the autoclave and the current taken from the supply. Here, we are giving megajoules is what? We are giving the energy. We are giving the voltage. And we are giving with the minutes. Yes, they didn't give us power. They say we should find, autoclave use elements, heating elements. So we want to know the power rating of the heating element. If I want to repair an autoclave in my office, for instance, now, I will have to look at the rating of that element. Maybe the element is burnt and I want to get another one. I look at the power rating of that element. I will go to the market to buy the exact power rating of that particular element now. But now, I don't have the power rating of the element, but I know the energy based on experience, based on the log that I have with me, that whenever this autoclave is connected to power 250 watts, the energy consumed is 3.6 megajoules for so number. So I want to know the value of the heating element that I want to use. in power. So how do we go about it? We know that energy is equals to power multiplied by time from our definition. Power, okay, power, this is supposed to be energy is equals to power multiplied by time. So our power will now be equal to energy divided by time. This is divided by time. So which will give us, what is our energy? 3.6 times 10 raised to the power 6, you know, it's in megajoules. Divide by the time. What is our time? Our time is 40 minutes. We convert it to second, to 40 times 60. So by the time we do it, we get 1,500 watts, which is 1.5 kilowatts. Do we understand that? So the rating or the element that we want to use for the autoclave is what? Is 1.5 kilowatts. Now, what is the next question that they ask us to do? Let me check. And now say, find the, okay, and the current taken from the supply. So what is the current now? From our power, we know that power is equal to VI or IV, that is voltage and current. So by the time we do our manipulations, we know that I is equal to P divided by P from our power triangle. So our power is 1,500 and our P is 250 from the question. So we get 6 amps. Hence, the current taken from the supply is 6 amps. So we are, yes, 6 ampere, or you say 6 amps, depending on how you want to say it. The two of them are correct. So in our lesson time, we can try these 2 questions. So let's move ahead. Let's look at another component that is used in an electronic circuit, and that is capacitor. Capacitor, just like a resistor, the capacitor is a passive device and one which stores energy in an electric or electronic circuit. So in its basic form, a capacitor consists of 2 or more parallel conductive plates that do not touch each other. And this is the construction diagram of a capacitor. So we have 2 plates that are not touching each other. You put a dielectric material, something like an insulator in between there so that they don't touch each other. Then you pass electric energy through it. So then the capacitor through the 2 plates, they now charge up. So this is the symbol of a capacitor. This is the symbol of a capacitor. This is just the construction of the capacitor. You need to pass a direct current through the capacitor so that it can charge up. So when it is charged up, you now use it in an electronic or electric circuit. Our fan at home, it uses capacitor. If the capacitor is faulty, the rotation of the fan will be reduced. Our electric motor, the one that we use for pumping system, it also use capacitor because it stores the required energy, maybe to start the pump and also to keep the pump running. So capacitor construction. So we can read that. I've made the summary. Now let's look at the capacitance of a capacitor. What do we mean by capacitance? That is the capacity of that capacitor. How many microfarad or farad of energy can it store? So the unit of a capacitance is in farad with the capital letter F, named after a British physicist, Michael Faraday. However, farad is very large unit of measurement. So submultiple of Faraday are generally used, such as microfarad, which is times 10 raised to the power minus 6, nanofarad times 10 raised to the power minus 9, and picofarad times 10 raised to the power minus 12. Capacitor in parallel now. So the same way we have a resistor in parallel, we also have a capacitor in parallel and also capacitor in series. But we need to note all this so as against what we have in the resistor. So capacitor are said to be connected together in parallel when both of their terminals are respectively connected to each terminal, just the same way we have it in resistor. Then capacitor in parallel, the difference between them now, capacitor in parallel have a common voltage, the same way we have it in resistor. Vc is equal to Vc2, Vc1 is equal to Vc2, Vc3, and so on. So in the following circle, C1, C2, and C3 are connected together in parallel. Let's look at the circuit. These are connected in parallel. But when we have parallel connection of resistors now, we find the reciprocal, say R1/RT is equal to 1/R. But in terms of capacitor, it is opposite. Our C total is equal to C1 plus C2. It's just like you are doing it in series now. I hope we are following. So it's like we are doing it in
Yes,
series.
sir.
Yes, but it only applies to capacitors in parallel. So the same way, when you have capacitor in series, that is when you now find 1/CT is equal to 1/C1 plus 1. You now find the inverse of it to get the capacitance. So that is, so you can say
It's
when you have
opposite.
find the equivalent capacitance of the capacitor for capacitor in parallel connection, is just the opposite of what we have in resistors in parallel. And the same way, when you find the capacitance of the capacitor for capacitors in series connection, is the opposite of what you have in series connection for resistors. So this is just the example for a parallel connection. CT just C1 plus C2, just add it together. And one thing we need to know, as we noted for resistor, one important point to remember about parallel connection of capacitor in cycle is that the total capacitance CT of any two or more capacitors connected together in parallel will always be greater than the value of the largest capacitor in the group. And in our example now, look at our example. The equivalent capacitor of the capacitor is 0.6 microfarad, which is what is greater than the one that is the greatest. The highest value we have is 0.3. So when you look at the equivalent, it's greater than 0.3 microfarad. So if you have otherwise, you can fully check the value of my capacitor. Is it greater than the highest value of the capacitors that we are? Then you know that you are correct. But if it's lower, then you need to check your calculation again. So I've said this one too. For capacitors in series, the voltage is what? The voltage will drop. Just the same thing we have, the same way we have it in resistors in series. But the current is what? The current is the same. But the equivalent capacitors now, we will have 1/CT plus 1/C1 plus 1/C2 plus 1/C3. So let's look at the example now. We say taking the three capacitor value from the above example. So from the example that we use for capacitors in parallel, we can calculate the total current, the total cycle capacitor for the three capacitors as 1/CT as this. By the time you calculate it, you get 0.055. But what do you want to take out of it? What you want to take out of it is that one important point to remember about capacitors that are connected together in series configuration is that the total cycle capacitance of any number of capacitors connected together in series will always be less than the value of the smallest capacitor in the series. Look at what we get here is 0.05. The smallest value of the capacitors here is what? Is 0.1. And we are having 0.055, which is less than 0.1. That means at least that one has given us a clue that our answer is near to correct than to being wrong. So we are rounding up gradually. Let's look at diode. Diode are unidirectional semiconductor. You know, at the beginning of the class, we look at resistivity of materials, and we say there are materials that have property in between conductor and insulator, and these materials they are called semiconductor. So they are unidirectional semiconductor device that will only allow current to flow through them in one direction. Thereby, they are acting like what? Like a one-way electrical valve. That means they are forward biased. You apply the voltage to them through the positive terminal. But before we have a look at how signal or power diode work, we need to first understand the basic construction and concept. So diodes are important for a single piece of semiconductor material, which has a positive. When we are constructing diode, for instance, we have the positive region, which we call the host, and the negative region, which we call the negative region, we call the N region. So let's look at these. I decided not to go into the details of construction of semiconductor diode. So these are examples of diodes that are used in electronic circuits. They usually come with numbers. So they are numbers that you use to buy them in the market. The one that is have SIM, when you SID, S1G, S1M. So when you get to the market, they will use the number to get you the type of diode that you have. So semiconductor materials are materials like silicon, germanium, and gallium arsenide. So they have electric property somewhere in between the middle of conductor and insulator, just like what I have said. But just brief introduction to how they work and how they are constructed. So they are good conductor. They are not good conductor nor good insulator. So they have property in between the two. However, their ability to conduct electricity can be greatly improved by adding certain impurity to their crystalline structure. So by controlling the amount of impurity that is added to the semiconductor material, it is possible to control their conductivity. These impurities are called donors or acceptors, depending on whether they produce electron or hole. So the process of adding impurity atoms to semiconductor is what we call doping. So the p-n junction is talking about connecting a diode, a semiconductor in a forward bias manner. This is an example of forward bias. You connect the positive region to the what? To the positive region of the diode. This is the diode. This is the schematic diagram or symbol of a diode. We are still going to talk about circuit diagram in our next class. So we are going to look at all these different symbols for different electronic circuits. So the diode is one of the simplest semiconductor device which has the characteristic of passing current in one direction. However, unlike a resistor, a diode does not behave linearly with respect to applied voltage, as the diode has exceptional one-foot relationship. So we also use Ohm's law to calculate the value of diode is also rated in ohms. If you want to buy it, you want to know the value to use in a circuit now, it's also rated in ohms. So Ohm's law is also applicable to diode. So this is just the way they are constructed. This is the P region, this is the N region, positive region, negative region. Then you connect it. The positive region is connected to the positive terminal, and the N region, which is connected to the negative terminal. So by the time you now influence their electrical property, you can now generate a device or diode or semiconductor, which can be used in an electronic circuit. So we have different of diode. We have Zener diode. We have light emitting diode. We have like the other one that we mentioned under transistor. Under resistor. By the time you you add resistor and light together, you have a light resistor. The same thing applies to diode too. We have light emitting diode. So we have two modes of connection of a diode: forward bias and backward bias. Forward bias means you connect the positive terminal to the positive terminal of the DC power source, whereas the negative, the reverse bias is that you connect the positive terminal to the negative terminal of the voltage source. And that is where we are going to be stopping for today. So far, so good. We have been able to spend 1.5 hours for our lecture this morning. So on these notes, I want to entertain any question from whatever we have taught so far this morning. Do you have any question? Good morning.
Yeah, my name is Adam Solojedi, sir. Thank you for this lecture. It's actually taking us to become a small electrical engineer on our own here. Sir,
Right.
what exactly is the function of the diode? What are they used for?
Okay. Thank you so much, sir. Yeah, diode, just like a resistor that we talked about, is to limit the voltage, let me say the current now, to limit the current that is going to a particular circuit. That is why we said they can be forward bias and they have different applications anyway, but in the simpler form of it, they also act like what? Like a resistor to resist the flow of current, so that you don't have excessive current flowing through a particular circuit. Current is one of the most things that spoil our electronic circuit. So there is a need for us to get something that can limit the current that is going there. Then other than that, diode, they have different applications. When we talk about rectification, for instance, when you are converting AC to DC, you use diode to do what? To get a constant voltage.
Okay.
Yes, you use a diode to get a constant voltage. And also we also have what we call Zener diode. So this Zener diode, they produce a constant voltage. Let's say you have a 5-volt diode, Zener diode, for instance now, and you want to maintain a 5 volt to a particular device. All you need to do is just to get that Zener diode of 5 volts with other specifications in place. So you continue to get a constant voltage of 5 volts to that particular circuit. We also have what we call light emitting diode. Their own application is to indicate light.
Okay.
They will show light when current pass through them. So you can use them as a switch, for instance, now, or as a monitoring device. I want to know this device is working. Once you see the light of that diode, that light emitting diode coming on, know it's working. So if there is no light on it again, maybe probably something has gone wrong. So diode, they have different applications in electronic device, but majorly they act like a resistor to limit current that flows through the circuit.
Thank you,
Thank
sir.
All right. Do you have any questions? Any other question?
Sir, good morning, sir.
Good morning, ma.
Yes, sir. Thank you for the lecture. Please, my question is that, can we now replace the diode with resistor, or must the two of them stand together?
You cannot replace one for each other. Each of them is suitable for a particular application. So it is for us to now decide which one is suitable for the application that we are using. No, when you are talking about DC circuit, for instance, now, most especially you use diode most at time. diode will be suitable. But when you are using a direct, an alternating current, for instance, now,
Correct.
you might be needing more of a resistor.
Diode.
So you cannot replace each for each other. It depends on the application or what you are using them for. That will determine which one are you using, which one are you not to use.
Sir,
Thank you, sir.
good morning, sir.
Good morning.
Yes, sir. So can we say that resistance and impedance are the same thing, or they are just different? Because I'm mixing them up, sir.
Okay, you know,
Because
when we
impedance.
okay, I understand. When we started the lecture, we said that resistor, they resist the flow or impede the flow of current. So that is where the word impedance comes in. There's another electronic device that you call inductor. Inductor. We have capacitor, we have inductor. So inductor serves as an impedance that you are talking about. But the function of a resistor, you can say that it impedes. When you are preventing something, you are impeding it. You are impeding the flow of something. You want to absorb a larger amount of that thing to yourself before you now allow little to pass through you. So impedance is just the name. A resistor is a resistor. It's not an impedance. But we have an inductor. So when we talk about inductor now, in capacitor, we are talking about capacitors of capacitor. In inductor, we are going to be talking about inductance now. Now, it depends, it's now the name now. There's a name that is used for a particular electronic device. So resistor, resist. Capacitor is what is to store electric charges. And when you are talking about its capacity, you talk about capacitance of capacitor. In inductor now, you are talking about inductance of the inductor. But don't forget that the three of them, or all of them, they are serving a particular purpose in the circuit. So you cannot say that a resistor is an inductor. It's not an inductor. It resists the flow of, but you can say it impedes, but it's not an inductance.
Okay.
I don't know if you
Yes, I wanted to know whether it's an impedance. That's what I want.
It's not an impedance. Impedance is another electronic component.
Oh, all right, sir. Thank you, sir.
Yes, sir. And that impedance is coming from the one inductor. So we talk about impedance of the inductor as we have it for capacitor.
Okay, noted, sir.
All right, thank you.
Good morning, sir.
Question? Good morning.
Yeah, thank you for the lecture, sir.
Thank you.
Just a quick question, sir. A circuit can have a maximum of how many resistors? A simple circuit.
As many as possible, depending on the component that particular circuit is having. No, if you are having, let's say you are having a circuit, we are still going to come to schematic diagram and circuit diagram. You will see different type of circuit. You can have as many as possible. Let's say now in a circuit that you have a capacitor, you have a resistor, you have an inductance, you have a particular load. You need to have a CMOS battery. You need to have a CMOS battery. You need to have an alarm system. All these alarm system, CMOS battery, they will need their own different resistors because of the current that they want for each of these devices. So actually, you cannot determine this is the number of resistors that I want to have. It depends on the complexity of that particular circuit. You can have as many as possible. Please, let's meet ourselves. We can have as many as possible, depending on what that particular circuit wants to do. So it's not that you have to have a specific number.
Thank you, sir.
Yes, sir.
My Mr. Debi, you have a question, sir?
Yes. Good morning, sir. Thank you very much, sir, for the lecture. And the
Yes,
nitty-gritty of all these lectures is actually interesting. But
thank you, sir.
there's one circuit, one diagram circuit that was drawn that I saw when you are giving the lecture about all these charges,
Okay.
positive charge, negative charge. You said electron flows from negative charge, while current flows from positive charge. I'm getting,
Okay.
is it electron that is actually drafting the current, or what? I need little more explanation on that.
Okay, sir. Let me quickly go to the slide. Okay. Now, this is where you are talking about, what you are talking about. Conventional current flow. You know, the current flow from the positive. This is the positive terminal of the cell or the battery now. We are having two cells here, so we call it battery. This is the positive terminal. Current will flow from the positive to negative. But electron, on the other hand, which will generate this current, it will flow from the negative terminal. This is the direction of flow. It's that they are now opposing each other. It is the electron that will flow before the current can flow. Because we talk about conductor, semiconductor, and insulator. Insulator do not allow electron to flow through them. So when you apply a DC voltage source to a conductor, for instance, the electron has to flow first in that conductor. Is the flowing of this electron that will now generate the electric current. So the two of them, they don't flow in the same direction. So current flow from positive to negative, whereas the electron will flow from negative to positive. Electron must move first, because in our physics and in our chemistry, the electron that is in the outermost shell of a particular element now have to be excited. It is when it is excited that it will now move its position from where it's staying to another position within that conductor. So the electron has to move. It is the movement of this electron that will now generate current. The current will now flow in the opposite direction of that particular electron.
Okay. Thank you very much, sir.
Yes, sir. Thank you. Any other questions, sir? So thank you. I need to make one clarification as regarding our last lecture. There's one formula that I gave you on centrifuge, the calculation of centrifugal force. You know, I'm using slide, and that too that is there. I said centrifugal force is equals to mass omega 2r. That 2 is not 2, it's supposed to be omega raised to power 2. But because we are using slide, it has now make it to become 2. So it's supposed to be mass times omega raised to power 2 times r, where r is the radius, w is the omega, m is the mass. Please, let's take note of that. It is because of the PowerPoint that is now making it as if it is 2. It's supposed to be omega raised to power 2.
Okay, sir.
Please, let's take correction for that. Okay, all right, thank you. So, any other questions, sir?
Hello, sir.
Yes, sir.
Sorry, sir. Thank you very much for this one that you raised. I actually noted something about that example. It's
okay,
like
sir.
I'm trying to calculate it, because you mentioned that something has to be converted to second.
Yes.
When trying to calculate the value gotten was very high, very high.
Yeah.
Is it really compatible?
No. I just took that question off as we were having that lecture that day. So there's possibility of that figure being high, because it's not a practical question like that. I just took it off at while the lecture was going on. Not that the question was written somewhere. So I just dictate the question while we were having that class. So I just want to I just want us to have the application of that particular formula. So that is the essence of that example that time. So if at all, if I want to give any questions relating to that, I will have looked at it so that the value will be within the range, within the scope of what we want to achieve. So
Okay.
I know the value may be too high because that question, I just take it while we were asking that question. That is why it is like that. Just make sure that you understand the concept behind it. Conversion is very, very important. You convert from gram to kilogram, then you convert from radian. I think I gave you radian per minute, then you convert it to per second. All those kind of things. That is what I want you to take note, and then you use the formula appropriately.
Okay, thank you, sir.
All right, sir. So do you have any other question? So I would like to appreciate you. Thank you for at least finding time during this holiday to have the lecture today. At least with this lecture that we are having today, we are ahead of the confessional students because they have series of holiday. They said they have 1 week lecture free because all those things. So at least we are ahead of them now. And probably on Saturday, I think we should be having another lecture on Saturday. So I will communicate the class rep appropriately on that.
Okay, sir.
All right.
Thank you, sir.
Thank you, sir.
All
Thank
right.
you, sir.
Thank you, sir.
Thank you. Thank you. All right. Enjoy the rest of your day, sir.
Thank you.
Yes, sir. Thank you, sir.
Thank you for the lecture, sir.
All right. I will send the slide to the class rep now.
Yes, and it will be shared appropriately, sir.
Okay. Thank you.
You're welcome,
Class
sir.
rep,
All
the
right.
account number for logbook.
So for those of us, sir,
The account number you mentioned for logbook.
I will try and look for it and share it again. It's just that it will be so far away in the chat.
Okay.
Then for those of us who might want to recap this,
Okay.
I will share the YouTube link. What I did was to stream it to YouTube also, so you can go back as much time as you want and download it.
That's a very good one, sir.
All right, sir. Thank you. Thank you, sir.
Welcome. Sir? So there's no other information for now, but I will share the link on our group.
Ẹ bá wa sọ fún ìyá Adédàpọ̀ next time kó má fa ìfàkúfà sórí ìwé wa o.
Wọ́n láwọn ò mọ́mọ́ o.
A mọ̀ pé wọ́n mọ̀ ṣùgbọ́n wọ́n sí bẹ̀ náà.
Wọ́n ń try láti erase wọn orí erase mọ́ni.
Mo ti try o, ẹ má bínú. Fóònù ló ní issue ẹ lè gbé fóònù.
Mo ṣe báwọn ọmọ yín kan ló máa yí.
Mo ti try ẹ má bínú mi mọ̀ bó ṣe ṣẹlẹ̀ gan ẹ má bínú.
Understood.
Èmi ni omi ìmọ̀ bó ṣe ṣẹlẹ̀. Mo fẹ́ zoom slide yẹn kí n lè rí dáadáa. Mo kàn rí pé mo fà láti mo dẹ̀ try láti erase àwọn
Kí ló
sílẹ̀.
wẹ́ wá débẹ̀?
Ọbẹ̀ wo slide dáadáa ni.
Ọjẹ́ máa caution ọwọ́.
What is the characteristic of
Mi ò lo glasses mi so mo wá fẹ́ zoom ẹ̀. Ẹ má bínú. Apology please.
Ọwọ́ rẹ̀ wá nǹkan tí ò sọnù káàkiri.
Ẹ lọ gba gíláàsì o torí street àwọn yìí ojú ni
Ó
o.
ti scratch ni.
A tún padà sí physics class kọ́ lélẹ̀.
Ẹ ṣeun
Ọlá
o.
tún padà
No, physics electronics
sí
lélẹ̀.
physics class kọ́ lélẹ̀ current ampere yìí.
It's more of electronics.
Ẹyin physics guru.
Physics ni táwọn ọmọ mi kọ́
This is very
school náà
interesting,
lélẹ̀.
though. Honestly, it's very interesting.
Very, very.
Ó jẹ́ kí àwọn aránsí àwọn kan tó yẹn ti ṣe tẹ́lẹ̀.
Ó máa ń jẹ́ kéèyàn understand tó bá ń sọ wọ́n bá yí tún nǹkan ṣe gan-an kẹwò pé kí náà ṣe. Torí engineer ẹ má dé kọ́kọ́ máa bamboo wa pẹ̀lú kíní kan capacitor kíní.
Mr. Fasasi.
Yes, ma'am.
Can we have any other lecture today?
Unless Dr. Oni get across to me, he said it's likely we will have his lecture, but no time.
Okay.
That was before the last lecture, so I don't know whether he has changed his mind or he still wants to support it.
Okay, thank you. Yeah.
Ẹ káàárọ̀ ọ̀gá Òkètọ́lá.
Ẹ káàárọ̀ mà. Ẹ pẹ̀lẹ́ mà. Yes ma.
Mo wò ó pé bóyá ẹ̀ sí lórí kìíní tẹ́lẹ̀ mo wá lọ wò yín mo wá rí pé wọ́n mọ̀.
Àwọn tó kọ́kọ́ wọlé nìyẹn, èèyàn mẹ́rin tó kọ́kọ́ wọlé wọ́n wà lára wọn.
Torí àwọn ló máa ń rán wa létí, mo bá ní kó má jẹ́ pé àwọn náà ti gbàgbé o.
Tá bá fẹ́ pín gift ara wọn tó máa gba gift nìyẹn.
Okay.
Thank you, ma. Have a wonderful day.
Okay. Have a nice weekend. Thank you.
So I'll share the link on our group.
Okay.
Yes, for the YouTube. So in case we want to watch it again. Thank you.